of the gravitational constant of the density and then delta Z. So for B4, it's equal to, so the units for G are meters cubed over kilogram per second squared, right? And rho is grams per centimeters cubed. And delta Z is going to be meters. So first, what we want to do is we want to get rid of the units of volume. So we start by doing it's equal to, I'll write it down and I'll explain it. 1 over kilogram per second squared, which is this, times 1 meters cubed. That's when the conversion here comes into play. So we put 1 meters cubed converted into 10 to the 6 centimeters cubed. This entire thing here is for the gravitational constant. And now I'll do it step by step and we'll go G centimeters cubed times M. So we can cancel these out and we end up with 1 over kilogram second squared times 10 to the 6 times gram per centimeters cubed times meters. So obviously we can cancel out these units and we'll end up with 10 to the 6 over, I'm moving this up, over kilograms times gravity because I want to get rid of the units of kilograms next, of centimeters cubed times meters. So this is equal in terms to, so when you apply your kilogram conversion, you know that 1 kilogram is, so you cancel it out and you end up with, and you also cancel grams here, you end up with 10 to the 6 meters per second squared, which is equal to 10 to the third second squared of meters times 1. We want to get rid of meters because we're dealing with gauge and centimeters, so over 1 meter. When we get rid of that, we end up with 10 to the 5th centimeters per second squared. That's our value for the B. These are the units. Okay, so now the next step would be to, remember that this is Gauss, so it's also equal to 10 to the 5 Gauss. Next, we want to see how we got the derivation. Oh, sorry. Okay. Next, we simply apply the different values. So B4 is going to be equal to 6.67, which is G, times 10 to the negative 11, times 10 to the 5th Gauss. We don't need to put the units because all the units went into getting this value here, which is equal to 6.67 times 10 to the negative 3 milligauss. Finally, these are the units. Finally, we end up with B4 is correction is equal to 2 pi, this entire value, when you do 2 times 3.5 So if you're applying Bouguer correction, you just multiply this by rho, which has to be in grams per centimeters cubed as we saw here, and by Z, which has to be in meters. That's why you no longer have milligal per meter here. Does that make sense? Do you guys have questions?
So in the end, you add up the Bouguer, like delta G Bouguer and delta G free air
That's
together.
what is called the Bouguer anomaly. It's you have the gravity of the observed gravity. You subtract or add the latitude correction. You subtract or add the free air correction. You subtract or add the Bouguer correction, which is this equation here with the 2 pi, and then this entire equation is referred to as the Bouguer anomaly. That's the technical difference between correction and anomaly. Okay. Okay. So this is 2A. So I would recommend using either MATLAB or Excel, depending on what you guys are fluent with. But I did Excel so that I could show you guys the steps. So you are given the meters south. Ignore this for now. The meters south, the elevation, and G observed. Keep in mind that 1 G U, they call it gravity units, is the equivalent to 0.1 milligal. So you need that to do problem 2A. So you go from the observed gravity in GU, in gravity units, into milligal. Keep in mind that it's not times 9.8 meters per second squared or 981 centimeters per second squared. It's different. So it's 0.1 milligal. Next, you have the time, which we won't be using. Next, you apply your different corrections. So let's assume that the density of our walk is 2.7 grams per centimeters cubed. And here I showed you that I went from degrees into radians. So for latitude correction, you just put phi is equal to 42 degrees in radians here. And remember how I said it's in milligauss per kilometer? So you have to divide and go into meters, which means divide by 1,000 to get meters. And it doesn't really matter that you multiply latitude correction by elevation because it's not affected by correction. So it's going to be times 1 meter. So you'll get rid of meters, and this is going to end up being just milligal. And next, we do the free air correction. It's the formula I gave you earlier. It's 0.308, a bunch of other numbers, times elevation minus datum. So elevation, and then so our datum is at here. Let's pick that as our datum. So I did this equation like that so that you could end up with 0. When you do 139, elevation minus elevation, it gives you 0. And then for the next one, it's going to be this elevation minus your datum. The next one is going to be this elevation minus your datum, and so forth. Questions? All right. Finally, you do your Bouguer. It's just like I showed. It's still elevation minus datum times density of your rock. And you end up like for here, I actually put the actual signs simply because we're looking at going from north to south. So this is positive That's what I explained earlier for the Bugey and Fourier correction.
What did you say was we're gonna multiply by the distance differences for the latitude correction?
So yes, so the like I wrote earlier, the formulas for the latitude correction gives units of milligauss per kilometers,
Okay.
and everything else here should be in meters. So what we do is we divide by 1,000 kilometers to I mean 1,000 to so 1 kilometer is equal to 1,000 meters.
Okay.
You divide or multiply depending on which way you are more, um, you can do it faster or better. So you end up with milligauss per meters. So what I said is latitude is not affected by the elevation at this point. So you just multiply by 1 meters